Hello, NEET aspirants. Today, we will learn about heat, internal energy, and work. As shown in GIF, hot steaming tea is transferred from a hot container to a cup. We can see steam emanating from the tea as it is poured into the cup. In this simple scenario, something fascinating happening. Heat is subtly shifted from hot tea to the colder regions or surroundings. Additionally, when the same tea cup is left, its temperature decreases until it reaches the temperature of its surroundings. This natural movement of a heat between the objects of different temperature is what we call heat transfer. Building upon our previous discussion of heat transfer, let's explore further instances of heat transfer and its impact on internal energy in our daily routines. Even in our daily routines, we encounter instances of heat transfer and alteration in internal energy. For instance, when you pump air into a bicycle tire, you are infusing energy into the system by exerting pressure on the air molecules. This act increases their internal energy and interestingly cause the air to warm up, showcasing another facet of heat transfer. Now, let's explore the concept of internal energy, which represents the total energy stored within a system. Internal energy is the sum of a substance, kinetic energy, and potential energy, and it is the result of the motion of the substance's particles. Internal energy represents the collective excitement within the objects, stemming from the dynamic motion and arrangement of their constituent particles. It's akin to the unseen vitality pulsating within every material. Internal energy, represented as capital U, is the total energy stored within a system and results from the dynamic motion and arrangement of particles. This energy reservoir encompasses both kinetic and potential energies, reflecting the collective excitement within the objects. Consider a pot of water brought to a boiling on a stove top. As heat is applied to the water, the internal energy of the liquid increases dramatically. The water molecules become more energetic, moving faster and colliding with great force. Eventually, the internal energy reaches a threshold where the water transitions from liquid to a gas state, creating a visible manifestation of internal energy in action, bubbling, and boiling water. Additionally, if we add a cup of boiling water to a bucket of water at room temperature, heat will transfer from the cup of boiling water to the bucket of water, increasing the internal energy of the bucket of water. Internal energy, capital U, constitutes both kinetic and potential energies, serving as the fundamental aspect of thermodynamics. The dynamic equilibrium of internal energy is subject to alteration through two primary mechanisms: heat transfer and work. When heat is introduced into the system, the internal energy surges. Conversely, its removal induces a decline. Similarly, work exerted on the system augments internal energy, while work performed by the system diminishes it. Understanding these mechanisms not only unveils the intricate interplay of energy within the system but also underscores the fundamental principles governing the thermodynamic processes. In summary, the internal energy, denoted by capital U, encompasses both kinetic and potential energies of system particles, serving as a fundamental aspect of thermodynamics. Now let's apply our understanding of work and heat transfer to a real-world example, such as the Stirling engine, illustrating the principles of gas compression and expansion. Stirling engine as an example of gas compression and expansion, where work is done on the gas during compression, leading to an increase in temperature, and the work is done by the gas during expansion, resulting in decrease in temperature. In beta Stirling engine setup, a singular power piston and a displacer piston are situated within the same cylinder, both mounted on the same shaft. The displacer piston, designed with a loose fit, does not harness any power from the expanding gas. Rather, its primary function is to shuttle the working gas between the hot and the cold heat exchangers. As the working gas is directed towards the hot end of the cylinder, it undergoes expansion, propelling the power piston forward. Conversely, when the gas is directed toward the cold end, it contracts, and the machine momentum, often supplemented by a flywheel, drives the power piston in the opposite direction to compress the gas. Notably, the power piston remains insulated from the direct contact with the heated gas. Combining kinetic and potential energies, internal energy capital U constitutes the eternity of the energy stored within a system. The internal energy constitutes the entirety of energy stored within a system, arising from the dynamic motion and the spatial arrangement of its constituent particles. This energy reservoir encompasses both kinetic energy attributed to a particle motion and the potential energy derived from the relative position of particles within the system. In the context of gas, internal energy manifests as the cumulative kinetic energy of its molecules in the random motion, along with any potential energy arises from intermolecular forces. Unlike transient entities, internal energy stands as a state variable reliant solely on the current state of the system, irrespective of the path taken to achieve that state. It is the paramount to difference between the heat and internal energy. While heat denotes energy in transit, moving from the region of high temperature to low temperature, internal energy represents the total energy reservoir stored within the system. Thus, while heat and work can modulate the internal energy of a system, they are distinct entities from internal energy itself. Energy transfer mechanism in thermodynamics, focusing on heat, denoted by capital Q, and the work, denoted by capital W. Heat, a mode of transfer, spontaneously moves from hotter to colder objects until thermal equilibrium is achieved. When added to a system, heat increases its internal energy while its removal decreases it. Heat is typically measured in units such as joules or calories. Work, on the other hand, involves a mechanical energy transfer through displacement forces like pushing a piston or stirring a fluid. It can also alter a system's internal energy. Work done on a system increases it, while work done by the system decreases it. Work is measured in units such as joules. In summary, heat, internal energy, and work are crucial concepts in thermodynamics, each with distinct roles in energy transfer and system behavior. Heat, internal energy serve as a state variable encapsulating the total energy stored within a system. Heat, capital Q, facilitate the energy transfer between the systems, driven by temperature differentials and capable of altering internal energy, so it is not a state function. Work entitles mechanical energy transfer to or from. Work, capital W, entails mechanical energy transfer to or from a system via acting forces, also influencing internal energy dynamics. So, it is not a state function. A state function is a property that depends only on a current state of a system and not on the path taken to reach that state. Examples of the state functions includes internal energy capital U, temperature capital T, pressure capital P, volume capital V, and enthalpy denoted by capital H. As we conclude our discussion on thermodynamics, I, Avinash from www.genit.com, thank you for your engagement. Please consider liking, sharing, and subscribing to our platform. Until next time, happy learning. Hello, NEET